here today, I'm going to introduce to you to Anthony Brito. He's our developer of the software MAGMATH. And I hope you enjoyed the webinar. At the end, we're going to have some questions. So feel free to write down your questions. And at the end, Anthony will be pleased to answer all the questions that you have. So thank you and good morning.
Yeah, and we're going to try to keep it to maybe 15, 20 minutes of presentation. Right, so thank you once again for joining. Just a few words about MAGMATH, the company. We're based here in Unterhaching. We were founded in 2015 by Mauricio Esquerra and Ralph Luque. And the material that we invented and patented is a magnetic cement with, there you go. So it's an innovative concrete material that's created from cement and recycled magnetic particles, i.e. ferrite scrap. So we're really driving and contributing to the circular renewable economy. One of our main applications is the wireless charging of electric cars, and thereby a magnetic concrete really enhances the transfer of energy, and it's resistant and robust. So it has the mechanical properties of a cement, so it really can go in the street. We're not going to talk too much, or rather, about wireless charging today. Our focus is going to be on the other main application of our material, that is in the building and designing of customized inductors. And so in this next slide here, on the left, you see a video of, this is a standard test used in the cement industry to demonstrate the flowability of our material. So that's going to be the first important factor that makes it really good for customized inductors, as I'll try to explain during the course of the presentation. And on the right, you see the other important factor, which is that there's absolutely no pressing process required. So with MAGMATH, you really just pour and go, and that makes this whole process extremely cost effective, which is an important factor for us. So here we just wanted to show you what a MAGMATH inductor looks like in comparison with a standard toroid core. And so ours is a quadratic rectangular geometry, and here we only have the single phase pictures. Later you'll see some of our three-phase designs also. And the flowability of our material really is the base for our design philosophy, which we've called geometry versus material. So in comparison to more standard sort of Excel calculation tools that go through catalogs of inductors and combine them to provide you with a part, our philosophy is to really design each inductor as its new as a new component. And the way we do that is by optimizing all of the available geometry. So the MAGMATH material is both the core and poured around the core and the winding, thereby filling the whole space and enabling an extremely optimal magnetic field line concentration to achieve the desired electrical performance. And therefore this would be what we call a more integrational rather than differential design methodology. So instead of concentrating on material improvement at a given point, say in a core or at a point outside it, we consider the inductor as a whole. And the breakthrough here, and we're really proud of this as a company, was to offer this as an online software to really send this out to the customers and allow them to design their own inductors. And this is highlighted here in this video, just a schematic of the sort of process. So the user sends in just a few standard electrical data, which then run a live optimization of a design on the website. Right, and then you see here this process which I talked about earlier. So the winding wound around a MAGMATH core, which is then put inside a box, and then just more MAGMATH is sort of poured to achieve the exact specifications that are required. This is just the three main sort of factors that run the backbone of MAGMATH, which is the name of our software. The first is a hysteresis model that was developed by Mauricio Esquerra, and the link to the paper is in fact on the FAQ section of our website, so you can see his model there. We also additionally have a pretty advanced modeling of the winding that we use to accurately model the skin effect, proximity effect, and other such things. And then finally, to sort of be able to achieve this integrational approach that I talked about earlier, we utilize what's called a genetic optimization, and I'll show you a really nice animation in a few slides that indicates why this is useful for the type of design process that we have here. And so that's on the left side of the screen, and on the right, because obviously every model is only as good as its application in the real world. We have the comparison of our model. So the modeled L versus I curve versus the tested curve. And I just want to point out that this plot was actually generated. The tested curve rather was generated using a three-phase device a device to test three-phase inductors that we developed in collaboration with EDK. So all of you who are attending the presentation will receive a copy of this by email after, and the link. I hope my mouse works. The link here will sort of be available to you then, and you can check out the product. So that's another thing that we've developed in-house. So let's talk a little bit now about the interface of the website itself. For those of you who have used MAGMATH before, you'll notice that this is a new interface, and indeed this is something we've been working on in the last couple of months. Since MAGMATH 1.0, based on the feedback we received and our own sort of experience in the time since then. So now, well, the first major thing is that the inductor is now going to be designed right on the homepage itself, and we've streamlined the number of inputs to make the process much more intuitive. So for those of you who are familiar with the older version, the dimensions and some of the additional loss parameters that could be input have been streamlined, and now we're calculating much faster internally. So let me just walk you through the inputs. So right at the top, you have the inductor type, and you can choose AC/DC, and the design single or three, and I'll show you a comparison of those two designs later on in the presentation. So we need three mandatory inputs to run the problem, and the first two are kind of obvious. We need the nominal inductance and current. We need the working point. The next couple of inputs are to basically specialize or rather customize the curve, so you can specify an L0, and then for the losses you can specify an IRMS or a ripple if it's not in standard, and you see there the little subtitles do indicate that we have default values, so you can leave everything blank if you wish. The switching frequency is the other thing that we need to know, is the other input that is required to run a design. And then finally, the two additional optional inputs are the DC resistance, if that is a design factor that the customer wants to account for, and then finally the ambient temperature. We've allowed for a wide range because we do know that these inductors can be used in extremely varying situations, and the default is just room temperature. In the previous iteration of MAGMATH, we did have just a single submit button, and our philosophy then was to optimize always for cost. In this new version, we decided to change that up a little bit, and also give our users a chance to sort of see with the same electrical specs how a difference in geometry can generate a completely different inductor. So now we have three different options. We have a cost optimized, and then on the other extreme, we have a performance optimized. And so you're really talking about, small and light versus large and heavy, and you'll see that the performance really scales non-linearly, so you get a lot of bang for your buck. If you decide to go bigger, if having a lower temperature or lower losses is really important for your application, then you can do that now directly on the website. And then right in the middle, we also decided to give a balanced option, so someone who wants to sort of sit in between these two extremes. This is just a quick screenshot of the status page. This is what you'd see if you ran a design. On the left, you have your inputs with an option at the bottom to go back in case of typos or incorrect data. And then on the right, the status of the design that's currently being run. And then we've retained this option to submit your email, because these problems, as I mentioned, every design is a new one. And so we are running a live optimization for every calculation that you submit, and so it can take time. We've sped it up immensely since the last iteration of MAGMATH, and so most of our calculations do run in 2 to 3 minutes. But you can still submit an email address if you don't wish to wait, and then the result will be sent to you as soon as it's done. So let's go over to MAGMATH and run a problem. Just gonna pull my browser over to this page here. Okay, so this is the interface that we just talked about together. Sort of the standard test problem we've been running is just because the numbers are nice and the inductor sizes are sensible. 100 microhenries at 100 amps with a switching frequency of 10 kilohertz. And so let's just go ahead and run a cost optimized design. And you see it's so step 0 is here the initial problem analysis and sort of getting the parameters, analyzing the parameters so that we can send the optimization routine into the right place. And that's in fact what I want to talk about now while this problem is running. This design is running, excuse me. So in fact, earlier we had a 4 or 5 step optimization routine, and now we've just streamlined it down to 2. The first step is the most important, and this is a global optimization that takes place in a really high dimensional space. There are a lot of parameters that can be varied to generate a huge number of possible designs. And so what we need to do in this point here is to sort of play with the parameters to make sure that we find this working point correctly and sort of zero in on the right region of parameter space. And then, of course, if DCR is not entered, we do have internal checks to make sure that our designs are always sensible. And so this is the first step, and this is referred to internally. We refer to this as a global optimization. So sort of figuring out where this thing is going to be. And then the animation here was the one I talked about earlier, that showed the benefit and in fact almost the necessity of using something like a genetic algorithm in such a complicated design problem. And what you're seeing here is a sort of sped up version of what occurs. You start with a very large population of solutions that then evolve according to survival of the fittest, according to the constraints that we put in. And so this animation here demonstrates this highly complex well, it's just a 3D function a 2D function, excuse me, that has a very large number of local minima, and it's used as a test function to test the robustness of optimization algorithms. And the goal is obviously for the solutions to converge to one of the 2 deepest minima there. So you can think of this as like a multi-dimensional plot of costs, say, and we want to locate the minimum cost. And you don't want to get stuck in one of the smaller valleys, but you want to find your way to one of the bigger ones. And what you see in the animation is that the genetic algorithm almost always finds its way to either one of the 2 deepest valleys, which is exactly what we want. We don't want to get lost in higher dimensional parameter space, but we want at the end of the day the cheapest or the best performance or a balanced inductor that conforms to our electrical specifications. But it really, we can say with a reasonable degree of certainty that this is as good as we can do, and that's what the genetic algorithm allows us to achieve. This is done here in the meantime, so I can just show this to you. Yeah, and so this is an example of what you'd see for a standard test problem, as I say. You have here the dimensions, and the mass, the L versus I plot, and then some additional loss information on the right hand side. So the starting point of the curve, and then the loss information. And then here you can download the results as a PDF. There Yeah, so this, you can always save this as a reference, and if you are happy with the design, you send this number back to us and we can pull up that design and send it to you. You can also order a sample right from the website here. So just if you just submit your data, we receive a copy of the design that you ran, and then we'll be in touch with you within 1 or 2 business days with a sample offer. You can choose to run a new calculation, change these parameters. So if you're not trying to retrofit an exact part, but want to go, plus or minus 10 or 20 in either of these parameters, you can do that. Our software is free to use for as long as you want, and as many calculations as you want. So you can really take your time and zero in on the right inductor for your needs. And then finally, this was the new feature that we added. So I mentioned the cost optimized, the balance design, and the performance optimized. And obviously, we wanted to give you the option to toggle between these three. And so this will now run a balance design. And you will, at the completion of this problem, I'll toggle back to the browser in a minute. You'll see the two results side by side, so you can really compare the two. And I can show you this here quickly. Well, I guess that slide got left out. We can just wait for that to run. So this is the cost optimized in the balance, and you see we go from 2.5 kilos, 2.4 kilos to 5. So you go up in weight by 3, you go up in dimensions. But if we compare the losses, say you go from 5.9 milliohms, 32 watts and 127 to 2.9, 16 and 57. And then if you improve performance again, you get the final iteration. So you'd see another tab here that says performance optimized, and that would be still larger with a much lower operating temperature. In fact, in this case, it would barely heat up at all. Yeah, and for those of you who are accessing this on your mobile device, I just realized that because of the resolution, you might have to zoom in to read some of the numbers. But I hope that the concept is clear. And as I say, you must run these problems just to play with it and get a feel of what the software has to offer. I'll just run this here, so we can do a side by side of all three. And in the meantime, I'll show you the other comparison that we wanted to highlight, which was between the single and the 3-phase. And so in this case, this is the same test problem. And you look at the price range, for example. Oh, beg your pardon. It looks like this is an older version of the one of the slides didn't get updated. In any case, what I wanted to say, I'm not sure that we have the time to run this live now, is just a side by side balanced performance, say, of the single versus 3-phase would show you the cost savings in designing a 3-phase with our system as opposed to say using 3 single inductors side by side. Okay, this is finished. This is what I wanted to show you. So now you have the side by side of all three. 2.4. So we'll just look at the mass, for example. 2.4, 5.4, and then 8.3. So you go up, a certain factor in each case, and you save a lot in the losses. And then for each of these calculations, you can now you always have the result. You always have the option, to download the PDF or order a sample or run new calculations. I think as the last sort of point about this optimization process with regards to the genetic optimization is that we are in most cases optimizing a scalar function, so a single cost function, if you like. And so this means that in this higher dimensional space, there may be several geometries that correspond to an optimal cost of this particular function. And so in the case of, so what I mean to say is that you may notice as you run the same problem multiple times that there are differences in the length and maybe smaller differences in the mass, but that the price will always sort of land you in the same range. And that's just the trade-off that we have to make when using something like a genetic algorithm and playing in this complex higher dimensional space, is that guaranteeing a unique repeatable solution every time is not just not mathematically possible. And so you will notice small differences if you run the same problem again, but they will be minimal. Good. And this would be a good point to sorry, I just need to find the presentation again. Oh, okay. I guess I hit escape at some point and we exited. If you've seen all of this, I just have 1 or 2 slides remaining, and then we can jump right to questions. Yeah. Right. And this was the outlook. So I already talked a little bit about. For example, one of the last points you can read here is the access to the design library, and what we would like to do once the software kind of takes off and becomes more and we have a lot more customer engagement, is to compile a library of popular solutions so that this repeatability issue that I just talked about is we're able to handle a little bit better, and say if there are standard or popular inductor designs, we can sort of do internal checks and come up with the best possible one and offer that without any live optimization. So that would be one idea. But let me start from the top of the slide. We want new material grades. So Dr. Ralph Luca, who's our chemistry expert, is working on higher material grades. So higher permeabilities up to 75. Our current material permeability is 40. The data sheet, there's a link to the data sheet in this presentation, which you'll receive, but it's also immediately available on our website. So we're aiming to go higher in permeabilities and lower in losses up to higher frequencies in the megahertz range. And then, so that would be on the material side. And then with regards to the software, we're thinking about how to implement custom windings, because that has been a request. Custom geometries even, because at the moment we do only offer the rectangular geometry. Forced cooling, if you run problems that have a higher current, parts that are larger, you will notice that once you exceed this thermal class H, you will receive a warning on the software online, and that's part of the checks that we have post problem. So this post problem analysis, just to make sure that we're always offering a part that's feasible and physically sensible. So since we do have that check, we're trying to figure out how to implement cooling if a customer already has a solution for that. But that's of course a little bit challenging. And then finally, exact retrofitting. So sort of understanding how, if at all, it would be possible to really retrofit to exact dimensions. But this is a little bit of a challenge, just from a mathematics standpoint. And the final point here is that we really welcome your feedback. We really welcome your engagement. And if you notice, issues, or if you just have general feedback, or if you really like the software and want to tell us we did a good job, feel free to write to us and yeah, definitely tell us how we can be better. Any and all feedback is welcome. So thank you for your attention. That's all I had planned to say. I'll be happy to take questions for the next 5 minutes or so. Yeah, and just as a sort of caveat right at the beginning, I'm an engineer and I understand inductors a little bit, and I wrote the software. But Mauricio is our expert, and he apologizes that he couldn't be here personally today. So if I'm not able to answer all of your questions in detail, I'll be sure to write them down and get back to you with a detailed response as soon as I'm able to speak with him. So with that, I'll turn on your microphones and we can have a conversation. Sorry, or you can unmute your own microphone rather, because I think if I turn them all on, it would be a little bit, loud. So if you have any questions, just feel free to unmute yourself, and yeah, and I'm happy to answer. Hi, Miguel. Sorry, I see your chat message, but we can't hear you. I'm not sure if
No.
can you try to say something again, please? Okay, if you're speaking, there's no audio coming through for some reason.
No, I cannot hear him either.
Um,
Okay, Miguel, you can type your question if you want.
yeah, if you can type it, if it's something quick, and we would really appreciate it. Sorry for the technical difficulty. I see your question. Um, so we've designed inductors that really go to high temperatures without getting into specifics. We can exceed. I beg your pardon. So for those of you who've not been who haven't read the message in the chat, Miguel asked what maximum temperature this kind of material can stand. The material itself is does will not break down at high temperatures. It's a concrete, but what is decisive here in the for the inductor design is rather the insulation that we can use. And so, as I mentioned before, the standard insulation that we offer is up to thermal class H, which is also kind of what we've seen as the standard here that people ask for. Once we exceed that, we do usually require cooling. So thermal class H is 180 degrees, and that's as high as we go without forced cooling. Though for most sensible applications, anytime it starts to get that hot, you already have cooling at that point. But if your question is specifically about the material, at what temperature the material itself breaks down, I would have to ask Maurice here about this. We've not encountered an application where that's been a problem. Um, as you can see as you will see on our data sheet when you receive a copy of the presentation, the temperature coefficient of our material is extremely great. So it really radiates heat extremely well, and you can see that, for example, in the example that I just ran, comparing the cost, the balance, and the performance. If you scaled up by a reasonable factor in dimensions, it dissipated heat extremely efficiently. So our material is good for that, but physics comes into play at a certain point, and if the currents are just too high, we do advise cooling, require cooling rather after a certain range. But I can email you also some more detailed information with regards to that. Thank you for your question. Hi, Miguel. I see you wrote one more question. Do you have any comparison with other known material components like ferrets or iron powder? Yes. So as I say, our material data sheet really explicitly um, makes clear all of the material properties. A side-by-side comparison, we can definitely get that to you. So a side-by-side material comparison, I can also send that to you. We do have this. Our partners at MB Electronics have compiled a great list of this, a great side by side. So I will send that to you. Is that what you meant, the material itself, or were you more interested in the material? Okay, great, thank you. Yeah, I can send you that information. Great. So we're reaching we have reached the half an hour mark. So we'll stay online for a minute or so for any further questions. Yeah, so feel free to ask if there's any issues that I haven't addressed.
Okay, thank you very much, everybody, for joining. Feel free to go to our website at magmen.de or also to our website magmen.de to find out more information. We'll forward you a link to download the presentation if you wish. Also, we're gonna upload the video of this webinar. So for the people who arrived a bit late and didn't get a chance to see the whole video completely, the video will be uploaded shortly. So thank you again, and everybody have a nice day.
Thank you for your attention, and we're looking forward to your engagement with the website.
Thank you.
Thank you.